To introduce someone who I think a lot of you already know, it seems, but I just met her this morning, Marcia Lynn, who's here from the University of Berkeley, where she's a professor in the School of Education. And her talk really ties nicely to one of the points that Alfred made about assessment and how that's a very important part of this whole equation. And so she could speak about a lot of things. You should read her list of books that she published in her biography that you have in your folders. So lots of things around technology and science. So Marcia, thank you.
Thank you very much. That was a very inspiring talk. I'm frightened to go next, but I want to thank Alfred for sort of getting us into the mode of thinking about, the directions that we can go with technology and education. And I was asked to really help you understand some of the opportunities with technology and assessment. I'm sure that many of you are concerned about this, and this is a common obstacle that we all face in trying to really innovate in the current public school setting. For example, this is an actual item from the California State Assessment. Which of the following best describes an atom? Proteins and electrons grouped together in a random pattern, proteins and electrons grouped together in an alternating pattern, a core of electrons and neutrons surrounded by electrons, a core of electrons and neutrons surrounded by protons. What do you think the message is that this item sends? What does that tell you about what science should be?
One right answer.
One right answer, okay. What else?
Facts.
Facts, okay.
There's a very explicit, clear, single arrangement that things find themselves in when there isn't any variability.
No variability. Science is, it's clear.
Vocabulary.
Vocabulary's good.
Always pick C.
Always pick C. Excellent. He's from Berkeley, too. How do you get to Berkeley? Pick C. Oh, no. So is this what we want? I mean, first of all, how would we best get the answer to this? I mean, Google's really helped us, right? We could find this answer quarter of a second. There was a great Doonesbury cartoon where, someone was trying to answer the questions, and the other character was just entering the question into Google and getting the answer in 0.0001 second. So who needs education? Who needs science education? So I think that in contrast, of course. What do we really want people to understand and learn? I mean, what are the problems in science that people need to face? And what do you want your students to be able to do in your science class? Carrying this around. Does this work? Is that helping?
Yeah.
Oh, good. Okay. And it's not interfering. It's very exciting. What do we want? What do we want students to actually learn? What's the goal here? What problems should they be able to solve? Yeah. Training people to do science.
To be creative, to explore, to discover.
Creative, explore, discover.
To be engaged in the scientific process itself.
Use the scientific process.
But in this case, to understand the actual model of what an atom is and how we came to know that sort of phenomenological.
So there's a different thing that they should know, and this question is sending the wrong message. It's asking you to learn something that isn't important instead of the things that we really want people to know. And fundamentally, we want people to be lifelong learners because every day, right now, we hope people would have a better understanding of economics. But they could reason about some of these things. That's hard. We've got global climate. I have a wonderful set of videos for you to contrast the various opinions about it. But how do we teach people to sort all these messages out? I mean, it really is a complex challenge, and we want to change education so that students are prepared to do that. And so I would argue that we really want students to be able to integrate their ideas, to make sense of the world, to construct understanding, and I think that's what all of you were saying. And fortunately for me, we just wrote a book. I wrote a book with Batsheva Alan, which actually kind of pretty much builds on the kinds of messages that I read that all of you submitted with your applications. It's basically contrasting kind of how people sort of in the past have viewed that everybody absorbs understanding to the kind of model that I think we all want to implement today that really makes people able to construct their own understanding, to build on what they know, and then to sort that out, to get rid of the distinguish the ideas that they have maybe from the normative ones, and ultimately sort out their ideas and come up with more normative understanding of really the more complicated things, not which of the following best describes an atom, but actually how can I think about global climate change or energy conservation or any of the issues that we're currently facing in science. And fortunately, I think for all of us, there's really a strong movement to ensure that every school and every student has a computer. But I think you will all agree that right now in California, this just isn't the case. So I want to get that out now. I know that's true because I work in schools every day. I know that you have 40 students in your classroom and they hardly fit in the classroom, and you had to give away some of your computers because you couldn't get the school kids and the computers into the school. I understand that. I work with those schools. But I'm still optimistic that if we can get the computers into the schools, we should be thinking about what we can do with that. And I think that is really our best approach at the moment. I've been working for many more years than I'd like to admit to try to find a great way to essentially create an open source, free, available, and customizable resource for teachers. And this is, I think, for science, an absolutely imperative goal. The last speaker really emphasized the need for customization, and I wasn't planning to talk about that, but we do have some really marvelous data showing that teachers can build units in this web-based inquiry science environment. How many people are familiar with WISE? Lots of you, good. WISE 4 is just out. Actually, we rolled out our new website last night. I told my team that we had to get the new website out before my speech this morning. I think it was maybe 8:27 that they rolled it out this morning, but they claimed it was last night, but whatever. But we wanted to really make WISE 4 available for everybody to look at. We pilot tested it last year, and we have some really stunning results from students using it. And this summer, we just had a workshop where teachers looked at their student work from last year and customized the units to make them stronger. And this model, we've already shown, not only works for teachers to feel that, they're able to get their ideas into the curriculum, really connect to the things that they taught in the past, but it has phenomenal benefits for students. We have between a half and a full standard deviation gains when teachers make these kinds of customizations. And I mean, that really makes sense because you know your students. Teachers know their students. They've been working with them all year, and they know they're going to be similar next year. And so if they can really build in features that are based on what students were thinking last year, then they can be more efficient and more effective the next year. So, but that brings us to, well, what are we measuring? So if we're trying to teach them, what is an atom, that would be different from if we're trying to teach them to solve the problems of the future. So we've been thinking about how do you measure knowledge integration, and I'm going to show you a whole set of different solutions to this question, some of which really require careful human scoring, and some of which I will show you ways that we're really building in automated scoring. And I won't have time to totally talk about how we can use that for guidance, which was certainly an issue that was raised by the last speaker, but I'd like to be happy to talk about that informally. So here's a kind of item that we've been looking at to help students integrate their ideas and develop cumulative understanding. Write a story about how the rabbit gets and uses energy from the sun. And we actually can give you a few clues here, but think about it. What would you say? How would you answer this question? What are some of the issues? There's some hints at the bottom. Where does the energy come from? Some places it might come from? Yeah. Photosynthesis, okay. That's a good answer. What?
Fusion reactions in the
Fusion reactions in the sun. Great, okay. That's an idea. What's some other ideas that students might want to bring to make an argument to answer this question? Thermodynamics. So this is an item that really causes students to bring together their ideas and develop an argument. And just to give you some inspiration, this is a seventh grade student's post-test response to this question. I have to say that the pre-test response was pretty vague. The sun creates energy through nuclear fusion, which moves through wavelengths in space until it reaches Earth. Most is reflected by the atmosphere, but a tiny bit makes it through, and even a smaller fraction is absorbed by the chloroplasts. They use it to rearrange CO2 and H2O into glucose, and by that process, it turns into chemical energy. Chemical energy is stored in glucose, and when the rabbit absorbs the plant, and thus the glucose, it gains the chemical energy. Would you be happy with your students if they wrote this? Sadly, not every student wrote quite that answer. But I still think a seventh grader, that's fabulous. And this is a 5-day unit on photosynthesis. The teachers would like it to be 3 because that's what the standards call for, to teach photosynthesis in 7th grade. But 5 days has really, we can't really do it in less than 5. And they're very happy with the outcomes. It's just the curriculum is so crowded that it's hard to find time for all the topics that need to be taught. And this is an example of what I was mentioning about customization, because this is our first cohort and our second cohort using this photosynthesis unit, and the teachers customized it the first year, and as you can see, students made greater progress the second year. It's also true that the pretest is a little higher the first year and the second year, and that's because the students were also emphasizing cumulative understanding and focusing more on energy in 6th grade. So the 7th graders had the benefit of what the students had learned in 6th grade. And these are fairly reasonable or respectable outcomes. Yes?
Do they use a rubric to score?
Yes, we have a knowledge integration rubric. It's the book that, this is sort of like a prequel to the book. I'm sorry, we're covering a lot of information, but we've worked rather hard over the years to create these rubrics. In the summer when we work with our teachers, we actually refine them. But we also encourage teachers to just give more precise feedback. We have a facility for grading that includes a place where you can store your own comments. We call them pre-made comments, and then you don't have to write them every time for the same student. And over the years, teachers have really built better answers, and they also share with each other. So it becomes more rapid to at least give feedback. And I'll talk a little bit about that towards the end. But we actually, of course, scored the stories for this study, and that turned out to be a success. But of course, not everybody is a great writer, and not every student really can express themselves well, especially at the beginning. We think this is a really important goal, but we want to give students multiple avenues to succeed and to express themselves. And so another method we've used for assessing this kind of integrated understanding is what we call my system, and this we built in collaboration with the Concord Consortium in Massachusetts. And basically, this tool allows students to build sort of a map of their ideas of how energy is transferred and transformed. And so students can use these icons, they can link them together, and they can indicate, although it's hard to figure out, you can't quite read it, but they can choose the kind of energy flow, whether it's solar radiation, heat energy, chemical energy, infrared radiation, or no energy. So they're able to express similar ideas using my system, and they can build, a full map of an answer to that very same question with these icons and arrows. And we are now able to automatically give them feedback on their maps. So this is a help, especially if you think that you don't have time to read all of those nice, lovely answers. Although I've actually myself found it very invigorating reading when you see what good ideas students have. So I hope that the teachers that you are preparing might find these two alternatives valuable. WISE is free and open source. You can run this. You can actually register and run this photosynthesis unit tomorrow if you'd like to, and you can also customize it. The second thing that we've really found to be important in kind of this kind of teaching is that these new visualizations of scientific ideas that are really becoming more available. How many people use visualizations when they're preparing teachers? Some of the science ideas. Yeah, lots of you do. There's really good stuff that's out there now. This is Molecular Workbench. How many know about Molecular Workbench? A few of you. And what we've been doing is looking at, well, how do these help students learn? Part of that knowledge integration process, this is a really good way to add ideas. Students can work with these on their own and come to a better understanding of the ideas. You don't have to lecture necessarily, although you might want to. That's always an issue. We'll talk about that later. But I wanted to give you a chance to actually look at this visualization and think about, what might you do to assess whether students learned from it? Because after all, that's what we're interested in here. And people complain that, maybe these visualizations don't help. And teachers and researchers need to know whether they do. So this is a visualization of oxygen. We've got water here, so hydrogen and oxygen. I'm going to run it a couple of times. We have several options. This is a space filling model. You could also do a wireframe, which I don't think you can see so easily, and a whole bunch of other wonderful things, but we'll stick with space filling. I just wanted you to know it's very, very flexible. So we can run it without a spark. What do you think is going to happen? What didn't we add without a spark? We didn't add energy, yeah. So, what's happening? Okay, well, we ask students to think about that, and then we allow them to kind of do a little bit of an experiment and compare what was going on without the spark to if we add a spark. And I apologize, this is really not the most perfect way to add a spark, but sort of reminds you that that's what happened. So now what's happening? Okay, so what I'm going to do is I'm going to reset this, and I want you to find a neighbor at your table, or your whole table if you want, and kind of talk about what could students learn from this and how would you want to assess it? What do you want to assess from this kind of learning? I'm going to run it with the spark over and over again, and kind of really pay attention and see if you can figure out what students might be able to observe in the course of doing this, especially about chemical reactions. So we're going to just give you a minute, so talk to your partners. You're good at that. You've been doing that for a while now. You might have to talk to this person over here. You guys could talk to each other. You must know each other. I know you're trying to plan your talk, but you really have to talk to your neighbor. I'm sure you need to talk to your neighbor. So I'm Marcia Lynn, and Hillary Swanson is one of my cousins.
So what did you just say about Massachusetts wildlife?
That's the Concord Consortium built this. So,
I'm on the board of Concord Consortium. Yeah. So where were you?
I'm at Berkeley. That was true.
And my son is
Good. Well, we'll get together. Okay, I'm going to run it once more so you can check out your predictions that you've been making. Okay, so while I'm running it a second time, what are some of the observations that people came up with? What are some of your observations?
They were moving faster. I'm thinking of how my fifth graders would have responded. And they start getting together. They keep moving faster.
What else do people observe? Observations?
I'm cheating. I've done this before.
Uh-oh, he's cheating.
Well, we saw that there was actually a couple of different stages of the reaction. It wasn't just H2 and O2 went to H2O, but there was HO intermediaries and things like that had to all bump into each other for some reason.
How many people noticed that? Good. What we find is it takes maybe 6, 7, 8 times for students to run it before they start to notice those things. We refer to the initial reaction as sort of deceptive clarity. I mean, kids look at it and they say, okay, now I understand chemical reactions. But then they have to really delve in to really look at what's going on, follow a molecule. What did some of you do? Did you follow a molecule? Keep track of one thing or another. I can run it again here. What did you notice about the red bar on the side? Went up. Could you see what it is? Kinetic energy? Couldn't read it, but you sort of inferred. Yeah. Right. So how would we assess this kind of understanding? What kind of things could students learn from this, and how might we assess that?
Ask what things stay the same and what things change when you have or don't have the spark.
So compare these two. So that's great. A comparison opportunity. What's different when you add the spark? Okay.
What questions do the kids have after having made some of these observations?
What questions do you have? What don't you know? Yeah, very good question. Yeah.
If students come to this representation with some knowledge of concepts like activation energy, then they'll know what to look for.
That's
so
right.
Prior knowledge is going to play an important factor in sense making.
Prior knowledge is going to help, or at least they might identify some gaps, then go back to want to look for more information. Yeah.
As a non-scientist in the room, I found that as a non-scientist here in the room, I noticed that the discussion improved my observation skills quite a bit. You know, having peers pointing out a few things made me then notice more things. So
Great observation. Well, thank you for that, because I do think that we find that the collaborative discussions are fabulous. I'm going to show you a discussion from some students in a minute. So these are all really excellent suggestions, and we've done many of the things that you described. One thing that we've done is ask students to use Wise Draw, one of the tools in the Wise software, to actually draw 4 pictures showing the four stages, 4 kinds of different stages that might be happening in a chemical reaction. This is a different one, so this is an extension activity from what you were seeing in the visualization. And this has turned out to actually be very revealing. I mean, some students, for example, believe that even though it wasn't what you observed, that they think they observed that every single atom separated from every other atom first, and then they all got back together. Some people, even though you didn't observe this, think that all of the atoms join into one giant glob at the end. Maybe they think that's going to happen after what they were watching. I don't know, but but this is very helpful for teachers because, of course, they maybe didn't know that all these different ideas were running around in the heads of their students. And as one of you said, I mean, one of the problems is this chemical equation makes it sort of seem like maybe it does all happen at the same time, and that isn't really accurate, and it's pretty confusing if you really try to go further in chemistry and understand what's going on, or even why that temperature bar isn't just immediately changed to full. And so all of those factors are important, and one of our graduate students, Helen Zhang, really studied this activity where you draw. She compared it to just exploring the visualization. As I mentioned, sometimes there's sort of a feeling of deceptive clarity when you observe it, and it was far more effective for students to draw and think about it and discuss their drawings. The discussions were very, very effective rather than to just explore. So this is sort of one of the things that's I think really important about assessment is that it's very formative. So, you know, you try different things and you figure out which ones are most effective. Another thing that she looked at was having students critique other people's experiments. What do you think? Do you think it would be better to draw or to critique? How many people think drawing would be good? How many people think critiquing would be good? Really interesting. I mean, she found that critiquing was as effective as drawing, which really surprised us. And the combination was really especially valuable for students. But when you think about it, of course, lots of times we don't critique in science. I mean, you know, it's like everybody tries to tell you, but of course now there's so much cacophonous information coming at you, we really have to become better critics. So one of the things that I think is really valuable is to help students develop more skill in critiquing their understanding. So I've been sort of running along the top of these slides some little icons that might have been just confusing. They're sort of part of that initial framework that I mentioned where sort of what's the pattern of knowledge integration? How do we get people to integrate their ideas? And so the first one that I mentioned was, that I highlighted on those little icons was eliciting ideas. And why is it so important to elicit ideas before we start giving new information? What do you think about that?
Tells you about misconceptions.
Get out the misconceptions. Know what people think.
I think sometimes the students aren't even aware of what they're learning, and they have to see what they thought before so they can actually recognize, wow, this is different than what I initially saw.
Yeah, so that if they don't think about what they already knew, then they might just add the information and think, oh, yeah, well, that's what the teacher wants, but I don't really have to think about it anywhere else. So getting the ideas out seems really important, and adding ideas, as I mentioned, one good way to do that is with visualizations. And then the final thing that I think is really important is that you have to get students to really engage these two sets of ideas. So we make predictions, and then we want them to distinguish ideas. I frequently tell college faculty that the single best way that they could go about actually I'm trying to find my movie here, go about actually improving their instruction would be just to have students make predictions. How often do you remember being asked to make a prediction in a college class? Does anybody ever remember being asked that? It's really fascinating how effective it can be. I don't exactly know why this is blank. Let's hope it's going to come out. Oh, good, here it is.
All right, let's put
Here's
downward
what
force.
Students discussing.
Yeah, it pulls it down.
Yeah, definitely.
Kind of conversations that we see in class.
It's like breaking.
Broken, yeah.
So they're looking at a more complicated chemical reaction.
Let's see what happens.
It's plastic. It's not going to go back.
So they're
I
really...
wonder if these are connected at all.
They're not.
No, this purple one's not at all connected. The green there's kind of bouncing off each other.
Temperature all the way up, see what happens.
It's gonna break it again. All right, let's try it anyways.
So that one of the great things.
You're so surprised.
This is something that I would probably play with at home over and over again.
See how many things you can do with it.
Yeah.
To add a lot of force.
Wouldn't you like your kids to say that they'd go home and play with it over and over again? Pretty exciting. These are high school students doing our detergents project, which is actually a polarity project where they look at how detergents help overcome the dangers to birds from oil spills. And really, this is in a school that where I guess it's 70% for your reduced price lunch. Really marvelous kids who just care so much about trying to, they're in a special, the academy where they volunteer to take all of the college prep courses. They were just working so hard on these, and it was so gratifying to see how they really accomplished their understanding of chemical reactions and other chemistry topics in that class. And I'd be happy to talk more about that. I just wanted to give you a few other quick notions. I know that my time is running out, of the kinds of things that the WISE environment would allow you to do. It allows you to log students' interactions with the visualizations and their writing. And so this is an example of where students are going back and forth between the visualization and writing their explanation. So this is what we'd like to see, and we can look to see whether that's happening. This is part of the sorting out of ideas that is so important, I think, for really knowledge integration. We also have tools when students draw graphs to actually filter their graphs so that you as a teacher can, quickly grade the graph because the software already identifies the kinds of things that students are not getting quite right in their graphs. we have a tool where you can flag student work. As you're going around watching your students, you can say, oh, that's a really interesting drawing, and flag it. You can flag a few, and then you can pull them up to do an opener, because we know that many of our teachers, how many teachers that you work, do you recommend that teachers do openers each day or every few days? How many people recommend that in their preparation programs? Most of you, yeah. So we really thought maybe we should think about what they're doing, because we observed that some of these openers were not really taking full advantage of the opportunity to open the class. And so we asked teachers to really flag work and then think about how to design their openers. And I think their first inclination was one that was completely not surprising. They wanted to pick the good, the bad, and the ugly. But then that turned out to be a really bad discussion, because it was all about, oh, you did it wrong and I did it right, and not about, well, what's the issue here? So we worked with them to figure out a good way to design openers, and we created sort of the knowledge integration opener, and teachers came up with some criteria about how to do that. And in the end, they led discussions where they did two things. I mean, first they showed all the examples, then they had kids just like we did here talk in small groups, and then they had a discussion, and that seemed to really be more effective. In fact, we found that the students who did the knowledge integration openers were far more likely to go back and revise the notes that they'd written in the past than those who didn't do the knowledge integration openers. Teachers can use this grading tool that shows that where they can, as I mentioned, make their own comments, store them, and then give feedback to their students. They can also, use it to compute grades and store information, etc. So just to summarize, we've looked at a bunch of different assessments here. We've talked about some of the advantages and some of the opportunities that they present, and I just wanted to focus on, sort of, first of all, what do they measure? We started with multiple choice, where most of you thought measured recall and facts. We've looked at science narratives, which I think definitely measure coherent understanding, but have some drawbacks from the standpoint of human scoring, although there's a lot of literature today showing that even if you don't grade at all student writing, if you just require them to do it, they actually learn from it. And in fact, you can ask them to write the same essay again in another few weeks, again not grading it, and they still learn more than actually getting feedback on multiple choice questions. So hey, go for it. They might hate you. That's one of the slight problems. We're exploring using latent semantic analysis to actually score these more complex essays, and that's looking like a promising technology. In fact, ETS uses it for scoring essays currently, and they use that and one human rater. And so there's an opportunity. That's a good thing for the future. Then we've looked at shorter explanation items. Those are quite easy to score. We're using C-Rater from ETS to score those, and that's great for post-tests and for teachers to be able to incorporate written assignments into their actual grading scheme, even if they have they have 40 students per class and 5 or 6 classes, so you can imagine how challenging it is to grade everybody's work. We looked at My System and WiseDraw, which really gives a good opportunity for grading, and finally graph construction. I didn't really show you any graph items, but I did give you some sense as to how graphing could work. So in conclusion, I guess I just want to emphasize that technology can help improve assessment because it increases emphasis on knowledge integration rather than recall. And these assessments that I've showed you are really for learning, right? I mean, you do the assessment, but at the same time, you're learning. So instead of wasting your time answering multiple choice questions that really it's hard to learn from them, it would be, I think, more practical for students to be doing learning and giving you evidence. Furthermore, as you saw, these items give us evidence every single day. So pretty soon, you'll have students who have a real record of a trajectory of what they've learned. They can go back and look at their previous thinking and be proud of themselves to see that they've made improvements. And as a teacher, you have an opportunity to really customize your instruction every day because you can see what your students are doing. In addition, at the end of the year, you can look over more of the work and customize your instruction for the next year. And because WISE is easily authorable, you can just go quickly, make changes in WISE, and then use it again the next year in a more effective way. Finally, automated scoring can help with guidance, and I didn't have time to talk about that, but thinking about how to guide students, what kind of feedback to give them is a really, really important question, and one that we're actively researching, and that I think is something that as a community we should be exploring. So as you're thinking ahead as to how to use these kinds of tools, there's really important questions. As I mentioned, even if you don't grade written work, students learn more than if they don't write. Sometimes feedback is not as good as actually just letting students talk to their neighbors and think about which might be the right answer. Finally, I just want to thank the TELS community. We have this incredible group of people, and none of the work that I've talked about today would be possible without all of their contributions. We have this brand new website. It's wise4.berkeley.edu. Please go to it, otherwise my staff will kill me. And as you can see, you can access any of these activities. Here's the photosynthesis activity. And you can run it tomorrow. Feel free to contact us. There's good information there about all the different opportunities that we have. So thank you very much.
We'll go ahead and take one question real quick.
Hi, I'd like to hear your thoughts on how to use technology to help students be more critical of their own learning and understanding, and also be critical of each other's when discussing groups.
Yeah, so one of the things that we're really interested in and concerned about is sort of monitoring your own progress. And as I said, because you can go back and look at what's going on, that's helpful. But we've found that even with that as a possibility, it needs to be built in. Teachers need to help students think about what have I learned and what progress have I made to become effective at self-monitoring. We've noticed that when students write explanations, they are more critical of themselves than if they just look at things or just do experiments. So I think in a way there's a flaw in active learning. I mean, everybody says, oh, active learning is great, but you have to be careful about active learning, because if it's just active, it's kind of, you think, oh, great, I'm doing science, I'm happy. Or students sometimes say to me, well, I'm getting an A, I don't have to think about it. So that's thinking about how you give guidance so that you don't convince students, oh, I'm getting an A and I don't have to think about it, but instead that, oh, I now understand this, but there's more to understand. So somehow balancing those things, I think that, we had sort of this feel-good feeling, in Doug Kirkpatrick, this teacher I've worked with for a long time, he used to just complain. He says, I'm sick and tired of everybody praising their kids. They need to give them guidance, not praise. But I think it's really important for us as teachers and teacher leaders to help our students realize the progress that they're making and what there is left to learn. And writing your explanations is really kind of a very good way for students to realize that there's gaps in their knowledge, because as soon as you start to write it down, you realize that there's flaws. And what we find is that over time, at the beginning, both teachers and students are kind of frustrated. In fact, we had English teachers coming to us and saying, look, English is in English class. Why are you doing English and science? Everybody's writing more in your science class than they're writing in my English class. And they're tired. They won't write in my English class because they already wrote in science. I'm saying, like, no, they need to do both. But I think that, and it's really amazing how good kids become at writing if they have practice. So thank you for your question.